in this question, we've been given two half-cell equilibria. They both involve iron. And our first question is, which half cell is going to go forwards and which one's going to go backwards? Remember, we're connecting these two half cells together. Okay, so there's got to be an oxidation half cell and a reduction half cell. And so one of these needs to go forwards, one of these needs to go backwards in order to get a flow of electrons. Okay, so in order to do that, we're going to use our line diagrams as we've used before. So we're going to draw my 0-volt diagram. I'm going to draw my line for my top one, which is the iron 3, iron 2 plus, and that is plus 0.77. And then my line for the iron 2 plus to iron solid is going to be minus 0.44. So this is my iron 2 plus to iron solid, and that is minus 0.44. Okay. And now we know that electrons flow from the more negative to the more positive, so I'm going to draw my direction of electrons flowing from iron 2 plus iron to iron 3 plus iron 2 plus. So we know that electrons are going to flow from the more negative half cell to the more positive half cell. Okay, so that means that the half cell that needs to be reversed is the more negative half cell. Okay, so what's going to happen in this half cell is that your iron is going to be oxidized to iron 2 plus, and it's going to provide the electrons to reduce iron 3 plus to iron 2 plus. So what I'm just going to do is I'm going to reverse this bottom half cell to make it go in the right direction. So iron solid is going to be oxidized to iron 2 plus, and it's releasing 2 electrons there. Okay, so that's all I need to do to answer that question. The more negative half cell is going to be reversed. So I need to now write the overall equation for this reaction. So to do that, I need to write my two half cells and write them in the right direction. So I'm just going to copy this straight off. We've already worked out that this one's going to be going in this direction. So AQ C minus, and then I can see the other half cell I need to write is iron 3 plus. Iron 3 plus an electron goes to iron 2 plus AQ. Great. Okay, so now to write the overall equation, I need to have the same number of electrons on both sides. And this side I've got 2 electrons, this side I've got 1 electron. So that's no good. I need to double this by 2 so that I've got 2 electrons involved here. So I'm now going to double that by 2. So I'm going to have 2 Fe3 plus AQ plus 2 electrons gives me 2 Fe2 plus AQ. Okay. Great, so I've now got equal numbers of electrons on both sides in my both half equations. What I'm going to do is now add equation 1 and equation 3 together. Okay, so 1 plus 3. So I've got Fe, so my left-hand side first, Fe plus 2 Fe3 plus 2E minus. So Fe solid plus 2 Fe3 plus 2E minus. Then add up the right-hand side, so I've got Fe2 plus. I've got 2 electrons, and I've got 2 more Fe2 plus. Great, okay. So now I've got my combined equation for this overall reaction. I know that I've got 2 electrons on both sides, so I cancel those out. And I know that I've got now Fe2 plus 2 Fe2 plus, that's going to be Fe3 plus, 3 Fe2 plus. So now I can simplify my overall reaction to get now on both sides. So I've got 3 Fe2 plus AQ. Okay, so I'm just going to double check that this balances out. I've got 3 ions on my left hand side, 3 ions on my right hand side. Good. 2 times 3 plus is 6 plus. 3 times 2 plus is 6 plus, so my charges balance and my ions balance. Okay, so that is the correct overall equation for the reaction. Okay, so I've now worked out the overall equation. The next thing I need to do is write the cell notation for this reaction. So in order to do that, I need to know that I put my more positive half cell on the right hand side. So if I go back here, my more positive half cell is the one that's plus 0.77 volts, and that is the Fe3 plus Fe2 plus equilibrium, and then my more negative is this Fe2 plus Fe1. So I need to put my Fe2 plus Fe on the left hand side, because that's the more negative one. So I know that the way we write our half cells is raw. So we have the reduced, oxidized, oxidized, reduced system here. So in my more negative electrode, I've got my Fe solid in a mixture, okay, with solution of Fe aqueous 2 plus ions. Okay, that's my left hand side. I then separate it with a salt bridge, and then my more positive half cell is going to go on the right, and that is my iron 3 plus and iron 2 plus equilibrium. So my iron 3 plus and iron 2 plus equilibrium. Iron 3 plus is the more oxidized species. It's got a higher oxidation state. So I need to put iron 3 plus AQ next to the salt bridge. Now I've got iron 2 plus as well in here, but that's in solution as well. So I'm not going to draw a line because that indicates a phase boundary. There's no phase boundary here because iron 3 plus and iron 2 plus are in the same phase. So I'm going to draw a comma instead. I'm going to draw my iron 2 plus aqueous. Okay, so I've now got my reduced, oxidized, let's draw it in here, oxidized, reduced species. And that is my cell notation for this. And if I'm told that I have a platinum electrode on this side for the reaction to catalyze this reaction, I've got a phase boundary between my ions in solution and my platinum, so I can draw that in at the end there if I'm told that there's a platinum electrode. So this is my cell notation for this overall reaction. And now the final step is to calculate the overall EMF. So I need to calculate the overall EMF of the reaction that we've just been doing. So EMF is equal to the electrode potential of the thing on the right minus the electrode potential of the half cell on the left. So the half cell on the right is my Fe3 plus 2 plus equilibrium, and then the one on the left is my Fe2 plus Fe. So EMF is equal to my Fe3 plus 2 plus, which is plus 0.77 volts. So that's plus 0.77 volts minus the electrode potential of my Fe2 plus equilibrium, which was minus 0.44 volts. So it's E of the right minus E on the left. Okay, so that's plus 0.77 volts plus 0.44 volts. Can I do that mental maths? That is 1.21 volts, I think. Plus 1.21 volts. Okay, so the overall EMF is now calculated using this equation. And we got that from my cell notation, where we know that the more positive electrode half cell is put on the right. And so I worked it out using this equation here.